In section 5.2, we're going to learn how chemists write and balance chemical equations. This is a pretty simple idea, it just requires a little bit of attention to detail. So we write a chemical equation with what we call the reactants or starting materials on the left of an arrow, which separates the reactants from the products. Pretty simple idea. As we mentioned previously, sometimes the reactants are referred to as reagents and also as starting materials. So those are synonyms for the word reactants. Commonly, we'll have multiple reactants and maybe even multiple products. When that's the case, the reactants and products are separated from one another by plus signs. So here's a good example here. We have hydrochloric acid reacting with sodium hydroxide to produce sodium chloride and water. Hydrochloric acid and sodium hydroxide are our reactants. Sodium chloride and water are our products. Often we'll indicate the physical state of the substance using the subscripts S, L, or G in parentheses. As I mentioned, these are written as subscripts. They're put in parentheses, and we always use the lowercase letter. Sometimes some people will not put the physical state indicator in subscripts. That's okay, it's generally considered acceptable, but you can see how it could be possible to confuse this as being part of the formula. So the subscript is my preference. We can also indicate whether a substance is dissolved in water to form what we call an aqueous solution by using the letters AQ in parentheses. So this is kind of worth doing to make things clear sometimes. Hydrogen chloride is actually a gas. Sodium hydroxide, when it's the pure substance, is actually a solid. Sodium chloride, the pure substance, is a solid. And water is a liquid at room temperature. So indicating that all of these things are dissolved in water, is very important here, because otherwise we'd be completely confused about what was happening with this reaction if we assumed that they were in their standard state at normal pressure and temperature. Something else that we'll do when we're writing a chemical equation is to use coefficients to indicate how many units there are of every substance. And the coefficients are placed in front of the formula for the substance. If there's only one of a thing, we don't give it a coefficient, because the fact that the formula is there means that there is at least one, so we don't have to indicate that. It's considered bad practice to include that additional one. Now, if a chemical equation is correctly written, it will be what we call balanced, and it will have the same number of atoms of each type on both sides of the arrow. So that is, it'll be written in agreement with the law of conservation of mass. So you can see that this first equation here, if I look at hydrogens, there are two on the left and there are two on the right. So it is balanced with respect to hydrogen. But when I go to look at the oxygens, there's two on the left, but there's only one on the right. So it's not balanced with respect to oxygen. This equation at the bottom has the correct set of coefficients. If I look at the hydrogens, there are 2 times 2, 4 on the left, and then 2 times 2, 4 on the right. In addition, if I look at the oxygens, there are 2 on the left, and then 2 times 1, there are 2 on the right. So both of the atom types present are balanced. So how we balance the atoms in a chemical equation is by adding one or more coefficients in front of some of the formulas. So all we do, so this equation here is not balanced, and I can show you why. The hydrogens there, we have 4 on the left and we have only 2 on the right. And if you look at the oxygens, you can see that we have 2 on the left, but we have 3 on the right. In this equation, those things have been corrected by the addition of these two coefficients. So sometimes you need one coefficient, sometimes you need multiple coefficients. it just depends upon the nature of the reaction. So the only way that we balance a chemical equation is by adding one or more of these coefficients in front of the formulas. We always try to make the coefficients the smallest whole number possible. So sometimes when you balance, your first attempt at balancing will lead to a set of coefficients that have a common multiple. In this case, it's 2. You should go ahead and divide by that common multiple so you end up with the smallest whole number set of coefficients. So let's have a look at balancing this equation here. You can see immediately that it's not balanced because we've got 3 ions on the left and only 1 on the right. So, and then also if we look there, we have 4 oxygens on the left and only 1 on the right. So you kind of know that it's out of whack pretty much immediately. So my strategy for balancing is to pick the substance that has the greatest variety of atoms. And so there's 2 things here. This guy's got 2 atom types, and this one here has 2 atoms, two types of atoms as well. So either of those 2 would be good. I'm going to go with the Fe3O4 because it looks like the most complex one. And then if I get that out of the way, then I've got the bulk of it worked out. So focusing on that guy, I can see that I've got 3 iron atoms on the left and only 1 iron atom on the right. So how am I going to get 1 up to 3? I'm going to have to put a 3 in front of there. My next difficulty is I've got 4 oxygen atoms on the left and I've only got the 1 oxygen atom over here on the right. So how do I get 1 up to 4? Well, I'm going to need to put a 4 in there. So having done that, it looks like this. Now the problem that I've got at this point in time is that now, so this is done, I've balanced for everything in there. So what I want to do now is move on to my next substance. And what I see now, my problem is that I've got 2 hydrogen atoms on the left and I've got 8 hydrogen atoms on the right. So how am I going to get my 2 up to 8? I'm going to have to multiply everything by 4, aren't I? So what I want to be doing now is putting a 4 in there. All right, there we go. So does it balance now? 3 iron atoms on the left, 3 iron atoms on the right, 4 oxygen atoms on the left, 4 oxygen atoms on the right. 4 times 2 gives me 8 hydrogen atoms on the left. 4 times 2 gives me 8 hydrogen atoms on the right. So everything is balanced. So if we look at our starting equation and compare it to our balanced equation, you can see that the only difference between the 2 is I added in these 3 coefficients. I haven't done anything to the formulas, I just changed the coefficients. So let's have a look at a more complicated one. So here we are, C4H10 plus O2 gives CO2 and H2O. C4H10 is an example of a type of compound called a hydrocarbon. It is composed of only carbon and hydrogen. So I'm going to start with the C4H10 because it has 2 types of atoms. It looks like the most complex formula. So I can see here that in C4H10 I've got 4 carbon atoms and 10 hydrogen atoms. So then I look on the other side and I see that I have 1 carbon atom and only 2 hydrogen atoms. So what I'm going to need to do is I'm going to need 4 lots of that, aren't I? And then I'm going to need 5 lots of that guy. So I balance for carbon by placing a 4 in front of the CO2, and I balance for hydrogen by placing a 5 in front of the water. And so it looks like this at this point, and everything in the C4H10 is balanced. So now I can move on to my O2. So when I look at my O2, I see that I've got 2 oxygen atoms on the left, and I got 13 oxygen atoms on the right. So how am I going to get 2 up to 13? Well, I'm going to have to multiply it by 13 on 2. 13 on 2 is just the same as 6.5, by the way. All right, so I'm going to have to put a coefficient in here of 6.5. So everything looks good now. I got 4 carbon atoms on the left, 10 hydrogen atoms on the left, there they are, and 13 oxygen atoms. 6.5 times 2 gives me 13. On the right, I've got 4 carbon atoms. 4 times 2, that's 8 oxygens, plus 5 oxygens, that equals a total of 13 oxygens. And then when I look at my hydrogen atoms, I've got 5 times 2 there, that's 10 hydrogen atoms. So everything is balanced, but the problem is that I've got a fractional coefficient for my O2. So we said previously that our coefficients should be the smallest set of whole numbers. So how am I going to get rid of my half there? What I'm going to do is I'm going to multiply everything in my balanced equation by 2. So I multiply everything by 2 to get rid of my half. So now I've got 2 of my C4H10, 13 of my O2s, 8 of my CO2s, and 10 of my waters. And everything balances, and I don't have any fractional coefficients in there. I can't get a smaller set of whole numbers than the 2, 13, 8, and 10. That's the best I can do. I can't divide through by a common multiple. So I've finished balancing. So a little kind of hint here is that often when you have a diatomic element, so that's H2, N2, O2, F2, Cl2, Br2, right? When we have one of those guys, or I2 actually as well, when we have one of those guys, will often, our first attempt of balancing will lead to a fractional coefficient, and we have to multiply through in this way to get rid of that fraction. Okay, so that concludes this video on writing and balancing chemical equations. Hopefully it was helpful.